Hi, folks. Today we are going to get into the specifics of sensation and perception, a very important unit. Combines a lot of concepts from, recently learned units about the brain, biological processes, and so forth, and things we've learned about cognition. So let's start with the basics: sensation versus perception. We're combining these two things into one unit, but these are two very different processes. Sensation has to do with us getting information in from the environment to our brains. We should use this phrase called bottom up processing. Bottom up processing is the basic biological aspect of sensation. So, using our senses, we have at least five basic ones, right? Seeing, hearing, touching, tasting, smelling. Those are the five senses. Those senses bring information in from our environment and send that information to the brain, our eyes, our ears, our noses, mouths, skin, whatever. That's bottom up processing, just purely biological, picking up energy, light, or sound waves, whatever, from the environment, bottom up, sending that raw information into the brain for processing. Again, that's bottom up processing or sensation. That's what we're going to deal with in this video segment mostly. But let's go ahead and understand perception as well, which we'll dig into more later. Perception is based on a lot of top down processing. Top down processing means that we're not just um, slaves to the raw information coming in from our environment. We're not only experiencing light information coming in through the eyes or sound waves through the ears. That's not the only stuff that affects our final experience. We've also got all these mental abstract things that affect our final interpretation. And that's where top down processing comes into play. Top down processing would involve things like our expectations, our preferences, our biases, our cultural experience, things that are going to affect our final perceptual experience. But those things exist beyond the biological, bits of information coming in through the eyes, ears. In other words, perception is a lot of times more than the sum of its parts. It's a phrase you'll hear sometimes. A quick example of that is, look, most of us, when we look at any kind of stimulus, take the background I've got going on behind me. It's one of the famous drawings from M.C. Escher, who's got all kinds of wonderful artwork drawings that he's created. All of us experience this sort of drawing or anything about the same way when we look at it. Okay, that's part of what we're going to be learning about here soon. Light bounces off a drawing like this. That light goes into our eyes, sets off a chain reaction of biological experiences that are fed back to the brain for processing. That's the bottom up stuff. And we all do that pretty much the same. Granted, there are some differences if you have color deficiencies, if you're red green colorblind, or if you have a visual impairment. But all that aside, most of us do the bottom up processing the same way as everyone else. But it's the top down processing that differs so much between us, right? 14 people can look at this drawing behind me and have 14 different interpretations of what's going on, right? Some people will say, that's really cool how that looks. Other people will say, this is stupid. I don't see what you're seeing. Somebody else is like, well, look at the depth perception and how he plays on this. We can't tell which way's up or down on these stairways. And somebody else is like, no, I can easily see that this guy's moving up. It's not messing with my mind at all. That's the top down processing. That's where psychology gets really fun, right? Trying to understand how we interpret things, why it's so different amongst people. So there's a quick introduction. We got sensation, which is mostly based on bottom up processing from the biological components, the environmental energies to the brain, just purely chemical and biological. But then you've got the perception piece, the top down processing. that involves all those abstract mental things we've been studying all year, like schemas and perceptual sets and cultural experience and all that stuff that can affect how we interpret those bottom up things that come into the brain. So keep all that in mind as we move forward, and let's jump into a lot of the bottom up processing that we need to understand. We're going to start with the skin senses. Just kind of quickly, I'm going to show you this image to guide us along, and do not think that you need to memorize these terms at the bottom, the specific names for sensory cells. We don't need the specifics there. We will when it comes to eyes and ears, but with skin senses, here's what I wanted you to see. I want you to start by understanding with bottom-up processing that all of our senses are affected by receptor cells. Receptor cells are a lot like neurons, but they're not neurons. They're not called neurons because these receptor cells, here we see them in the skin, they're not located in the central nervous system. Okay, neurons are only in the brain and the spine, at least where they're rooted. But these receptor cells that affect bottom-up processing so much, they start in the peripheral nervous system, outside of the brain and spine. So like your skin cells that we see here. You've got skin cells all throughout your body, in the periphery of your skin, obviously, whether that's skin in your scalp or in your hands and fingers or your legs, your feet. You've got skin cells all over, just waiting to pick up energy from the environment. But hold on one second. As I said, these receptor cells, they're a lot like neurons. They're going to be stimulated by something else, something in the environment. And every receptor cell will have something like dendrites, just like neurons, some way to receive information from outsiders. So again, receptor cells are messengers. They're going to pick up information from the outside world. And receptor cells, look at some of these pictures, they tend to have something like an axon, where they're going to send information to the central nervous system, where sensory neurons will pick up their signals. Okay, so receptor cells are a lot like neurons, but we don't call them neurons because they're in the peripheral nervous system, waiting to pick up information from the outside world, send that information into the spine and or the brain so that we can process it, bottom up processing, okay? Next thing we need to know before I get too much into this diagram is, here's a fancy term for you, ready? A phrase. There's something in psychology and in science called the doctrine of specific nerve energies. And it's a fancy idea, but it's pretty simple. All it means is we've got specialized cells in our bodies that can only pick up certain kinds of energies. Doctrine of specific nerve energies. So for instance, you've got receptor cells in the back of your eyeballs that can be stimulated by light energy. We're going to learn about that later, very, very soon. Okay? You've got receptor cells in your tongue, some of which pick up energies for sweetness. Some receptor cells will pick up energies for bitterness or sourness. We've got receptor cells in our ears that will, pick up information about sound waves. But all these receptor cells have a specialized job. Think of it this way: specific nerve energies. The receptor cells in your tongue cannot tell you whether it's light or dark outside. Try it right now. Just take a sec. Put me on pause. I'll be here. Have somebody come in your room and flip the light switch on and off while you've got your eyes tightly closed. But you got your tongue sticking out, and you're going to try to determine whether the lights are on or off in your room just by using your tongue. See if you can taste the amount of light in the room. That's weird. That ain't going to work for you unless you suffer from a disorder called synesthesia, which you'll read about in another assignment I've given you. Anyway, for now, you're not going to be able to taste whether it's light or dark in your room because the receptor cells that are in your tongue are specialized to pick up taste sensations: saltiness, sourness, sweetness, bitterness, things like that. Those receptor cells can't pick up the light, just like the receptor cells in your eyeballs are not specialized to pick up sound waves. You can't see sounds unless you suffer from synesthesia, which is a very rare sensory disorder. Again, very quickly, it's where people experience one sense as another sense. Could you imagine like eating a slice of pizza and being like, this tastes like triangles. It's really delicious and blue. Like this pizza is very blue today. You and I don't have a schema for how that would work for someone who suffers for synesthesia. They've got like neurological misconnections in their brain. So sensory information comes in and their brain misinterprets that information as a different sensory experience. That's weird. Obviously, it's a sensory disorder. But for most of us, our eyes have receptor cells that can only pick up light information. Our ears can pick up sound waves. The receptor cells are specialized to pick up certain kinds of energies. Now let's look at this diagram a little more closely. What I want you to see is that there are different kinds of skin cells, just to reinforce this idea that different receptor cells can pick up different kinds of energies from our environment. Look at this. In our skin, just in one little patch of skin, one little area, you've got some receptor cells that can pick up temperatures. And it might even be that some of these cells will pick up cold temperatures, and other cells right beside them might pick up heat information. Okay, so if you stick your hand in cold water, you've got certain receptor cells sending messages to the central nervous system saying, that's cold, that's cold. And in that moment, the heat cells that are right next door are chilling, they're just resting because there's no heat to be picked up on in that moment. You take your hand out and go put that same finger on a stove burner. Well, now the cold receptors are going to rest because there's no cold information being sent there, but the heat receptors are going to jump into business, sending heat information to the spine and the brain. All right. There are other receptor cells we have in the skin. Like, look, we have certain cells in our skin that only pick up pain signals. If we're stuck with a pin or something, okay, there's going to be a pain message sent to the spine and the brain for us to respond to. And look how that's a little bit different than these other cells that pick up pressure. So interesting that in any small area of your skin, you've got some cells that pick up this different information. So in other words, there's a very different experience if, I don't know, I've got an ink pen here. If I take this ink pen and just like press gently on my skin, maybe there are pressure cells there sending information to my brain and spine saying, yeah, there's something's poking us. That's kind of weird, right? Because apparently your receptor cells have a weird accent like that. But, if I put the point of the pin out and jam my skin very hard, it's not only going to be the pressure cells sending messages. All of a sudden, I'm going to have pain cells sending the message as well. And imagine if this ink pen was heated up on the end. Like I take a lighter and I burn the tip and then I jam it in my skin. Well, now I'm stimulating pressure cells and pain cells and heat cells. 3 different kinds of cells are going to be sending their information to the central nervous system so that I can process that information. And this is all happening unconsciously, faster than anybody can explain it, from the peripheral nervous system. See how important this stuff is? Bottom-up style even. Okay, one last thing about this. This will be a short video segment to introduce some sensation and perception. Not only do we have these special kinds of receptor cells, picking up certain kinds of energies from our environment, it also depends on, when I say it, I should say, the message we receive, the information we end up interpreting will also depend on the number of receptor cells firing and the frequency of those cells firing, like how often they fire. Remember, they're a lot like neurons, just in the peripheral nervous system. So, go back to my example. I've got my ink pen. If I just gently press on my skin, I'm activating pressure receptor cells. We understand specific nerve energies and how that's happening. But here's on top of that, what to understand. I'm not stimulating a whole bunch of receptor cells compared to if I take my whole fist and punch a larger area of my arm. Understand, this pinpoint is stimulating just a few receptor cells, and they're sending their message on to my brain. Well, just a few receptor cells, that's going to affect the overall experience I have. Like, oh, there's a little pinprick on my arm. That's weird, right? Like I feel that little point right there. But if something with a larger surface activates that area, now I've got more receptor cells from that whole area sending information to my brain, and that's going to affect my overall experience. Okay, so number of receptor cells firing is important, but also type of receptor cell firing is important. And now let's realize the frequency of firing is going to matter. If I just touch my arm, right? Even here, just gently punching my arm. This is weird. Maybe those receptor cells are going bazonk, 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 bazonk. Done. It's over. It's cool. Okay. But if I wail on my arm and punch really hard, those same receptor cells might go bazonk, 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 continuously sending those pressure and pain signals to the brain because of the greater impact. Frequency of firing is important. Okay? This even plays into, folks, a very important idea called sensory adaptation. Sensory adaptation, a very important idea for us to understand. If we understand that these receptor cells, start the process, picking up information from the environment, and their frequency of firing matters, now understand that these receptor cells, they're not going to fire forever, even if they're constantly stimulated. So, for example, you jump into cold water. Maybe it's summertime, jump into a pool expecting to be refreshed, but it's freezing cold. Look, you've got all these cold receptors, like over here, throughout your skin. Those cold receptors are going, bazonk, 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 sending messages to your brain. Dude, we're freezing. This is crazy. It's so cold. Bazonk, 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 to the brain. Cold, cold, cold. But here's an interesting thing about your body. Apparently your body's evolved to a point where if it's getting this like constant stimulation again and again, the brain's going to determine, if we personify the brain a little, the brain's going to determine, all right, eventually, look, I don't need to keep getting this signal. Like, calm down. Like, we haven't done anything about it, so just shut up. Because here's what's happened. You jump in that cold water, all those cold cells throughout your skin, throughout your body, are going cold, 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 bazonk, 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 cold, 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 right? But eventually, after a minute or a few minutes, those receptor cells are going to stop firing as much. They're going to get tuckered out. They're going to get exhausted. And it's like they figure, if we personify them a bit, they figure, look, brain, I've sent you the message. If you're not going to do anything about it, I'm going to stop telling you, right? It's like an annoying parent. I'm not going to tell you again, mister. We're cold. It's freezing in this pool. So here's what those receptor cells do throughout our body, okay? Cold, 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 because we just jumped in the pool. Cold, 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 cold. After a minute or two, cold, 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 we're cold. Couple of minutes in the pool, cold, cold. The frequency slows down. Cold, cold. Those cold receptors stop firing as much. And when they stop firing, we stop feeling as cold. This is sensory adaptation, where your receptor cells stop firing as much because they've been so stimulated for so long. They just get tired of firing. The body figures, the brain figures, we don't need this information, so shut up, kid. And the receptor cells stop firing their signal, cold, cold, cold. So we stop feeling the cold as much. We've been in the pool for a few minutes. The water temperature is still the same, but now we feel fine. We've adapted to the cold. Our friend comes up, hey, how's the water? It's fine, jump on in. They jump and freeze their toes off. They're like, dude, what the heck? You're like, it's fine after a couple minutes. That's because of sensory adaptation. Rewind that and make sure you understand how that's affected by receptor cells firing a bunch at first because they're stimulated by the environment. But eventually, with that same stimulation, they're going to stop sending their signal as much. Similarly, you walk into a room and smell something disgusting or hear a high-pitched noise or something, it's going to really bug you at first. But after you're there for a while, you're not even going to notice that same smell or that same sound because the receptor cells up inside your nose or inside your ear, they're firing a bunch at first. Dude, this stinks. This is terrible. It's awful. But eventually, they're going to go, stink, 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 stink. I mean, stink. Brian, if you're going to listen to me, I'm going to stop telling you. And that's why we all have a scent in our own homes that we're not familiar with, especially in times like in this corona quarantine. You're home all the time. You're used to the smell of your own house. You don't maybe think your house has a smell. It does. Not necessarily bad, not necessarily good, but when other people come to your home, they probably notice a certain smell that you don't notice because you've adapted to it. Sensory adaptation, a very real thing. Okay? Lots of information there. There's one last piece to understand with bottom-up processing. We understand the importance of the receptor cells. Now, let's look in the brain very quickly. We know that we've got a sensory cortex, this strip of cortex in the brain that has sensory neurons waiting to get this incoming information. Right in front of it, we've got a motor cortex over here. Okay, we're not talking about motor functions right now, but this diagram will make sense after I explain this one. We're talking sensory information. What this diagram, this weird diagram is showing us is how the brain, how the sensory cortex is organized with neurons. In other words, the pictures over here of these body parts show us how much of the sensory cortex is dedicated to that part of the body. Like how many neurons, generally speaking, relatively speaking, how many neurons in the sensory cortex are sitting there waiting for information from the different parts of our bodies? Well, if our body parts were sized relative to how much space they take up in the sensory cortex, we'd look something like this. Look at this. We would have ginormous lips and tongue, okay? That means that in the sensory cortex, there's a relatively large area dedicated to neurons waiting for information from the lips and the tongue. Similarly with the hands and the fingers. Relatively, there's a ton of surface area in the sensory cortex that's dedicated to neurons waiting to get information from the hands and the fingertips. Folks, this should make evolutionary sense, right? An evolutionary psychologist would say, duh, because that's how they talk, right? Duh. These are the parts of the body that are most important for getting information pertaining to our survival, right? Look, in the sensory cortex, for instance, there's not a huge area dedicated to the arms. The arms are a pretty narrow, small part of the sensory cortex. So in real life, we would have these little tiny, narrow, skinny arms, pretty small arms, relative, if that's how we were shaped bodily, to how our sensory cortex is structured. But again, evolutionarily, it should make sense because we don't depend on our arms to get information into the brain for our survival. Just like our head, our scalp, our forehead. We don't, like that's a tiny part of the sensory cortex that's dedicated to getting information from the head, from the forehead, from the scalp. Because folks, if we're going to get information about, I don't know, whether something's hot or not, if it's dangerous for us, what are we going to do? Walk up to that stove burner and place our forehead over it to see if it's hot? Or no, duh. We're going to put our hands out. We're going to use our fingers, our palms to see if that is hot, if it can be dangerous for us. Okay, so that's what this diagram is showing. Relatively speaking, the sensory importance to the brain, to the sensory cortex, the surface area dedicated to certain parts of the body. We can see, how this relates to evolution and our, current sensory experience. And just for funsies, if we were to actually look like the sensory cortex is set up, we would be something called a homunculus. That's a weird word for you, and brace yourself because this is weird. And if you ever see a guy like this coming at you on the street, run very fast in the opposite direction. Here's how he would look. Ah! Keep it to yourself if you know someone who actually looks like this. But here you go, right? Skinny, relatively small arms, giant lips and tongue, right? We've got ginormous hands and fingers, but kind of little tiny torso. You can't even see the torso. It's hidden by the lips there. This is just a reminder to you of how the sensory cortex is structured, how it dedicates surface area to certain parts of the body, the parts that are most important for the brain to get information from, at least tactile, touch information from, because, oh yeah, let's not forget, the sensory cortex is located in the front of the parietal lobe. The parietal lobe and the sensory cortex is getting our touch signals, information that's tactile. Okay, so when we look at the size of the lips and the hands and fingers, we're just talking about the skin senses. Okay, don't be confused when I say those are the lips, very important information to the brain. Yeah, for touch information, temperature, heat. We don't want to put something in our mouth if it's going to burn us or be super sharp and maybe kill us. So the lips are important bits of, sensory pickup there. Other parts of the brain we know are picking up other sensory information. So when I say these are the most important parts, to the brain, I'm talking just with touch signals, because the occipital lobe back here is going to pick up our visual signals and process vision. The temporal lobes over here on the sides of our brains are picking up our sound signals to interpret those. The parietal lobe, specifically the sensory cortex, is picking up our touch signals. There you have it, folks. We've got neurons in the brain picking up the information from those receptor cells in our peripheral nervous system. And we know how important those receptor cells are and how they can only pick up specific nerve energies from the environment and fire a bunch or a little bit, or have a lot of cells firing or only a few cells. Remember, just like a neuron, these receptor cells can never go buzz out, it's kind of cold, buzz out, like I'm firing just half speed this time. Jack, all or none. If these cells, just like neurons, if they're stimulated to fire, they're going to buzz out, do their thing, all or nothing. Catch you later with more stuff. Thanks, folks.